Hi everyone, my name is Steve Cosenza. I'm on the Finatra team at Twitter, and I'm here with Neuman, who's on the CSL team. And today we're going to be talking about streaming HTTP and how Finatra has used async stream to do it. Quick little summary of what is Finatra. Finatra is a framework for easily building APIs on top of Twitter's Scala stack. Right now, we support building HTTP services, but we have some internal experimental support for Thrift servers, and we plan to be releasing that at some point. Some highlights. Finatra has widespread use as Twitter's production HTTP framework. If you've used Finatra 1, 2 is about 50 times faster in many benchmarks. We have powerful feature and integration testing support, optional support for JSR 330 using Google Juice. We've got improved integration with Jackson over the normal Jackson Scala module. So we do things such as supporting required fields, default values, and validations on fields. You're also able to use that same kind of JSON support for declarative request parsing. So even if it's not JSON, it's a GET request, you still can do the type conversions and validations. And we have some nice integration with Logback if you're using that as your logging provider, which lets you do contextual logging across futures. OK, so here's what a request would look like in Finatra. To parse some JSON, you use a case class to mirror the JSON. You could see some of these annotations provide validation hints, such as a size. We have a default value for sensitive. Finatra controllers, you simply extend controller, and then you have methods for all your HTTP, get, post, delete, et cetera. In this case, we have posting a tweet and getting a tweet. And here you can see the batch versions of those endpoints. So on the top would let you post multiple tweets in one post. And on the bottom, it would let you do multiple lookups of tweets in a single post. And notice how the incoming argument is tweets, which is a sequence of posted tweet. And on the bottom, a sequence of tweet IDs. A server. You add filters, add controllers. On the bottom, you have a warm-up method so that you can get all of your clients warmed up, get the server JITted before you start accepting incoming traffic. And then here's an example of the feature testing support where we'll start up your server locally in an ephemeral port and make it easy to send in requests and assert responses. So on the sample that I showed you earlier, this would be what would happen if you posted a JSON body of a tweet that wasn't valid. And you could see, based on the validation fields, or based on the validation annotations, you'd get the errors below. So notice that it doesn't fail at the first one. It kind of collects all the errors and then gives them to you. OK, so what are the issues with the controller I just showed you? Mainly that we used a sequence for our tweets and tweet IDs. That's going to cause all of the data to be loaded into memory at once. And we're going to be increasing the latency of our response because we can't return anything until we've read all the tweets, saved all the tweets, and then return. So streaming to the rescue. Streaming, essentially, in this case, is going to be the incremental reading and processing of the request, and likewise, the incremental writing of the response. Now, traditionally, if you're using blocking APIs, this is pretty easy. You use an input stream if you're in Java to read your request. You use an output stream to generate your response. And then you probably have something like an iterator that you use throughout your program. However, in the non-blocking world, we need new primitives to be able to do this type of stream parsing. And for that, I will.
Cool. Hi, everyone. So yeah, as Steve was saying, what's really important for servers, I guess, is to not run out of memory. And one of the ways to do that is to sort of like bound your inputs. And streaming lets you kind of do that by turning something that's really big into like small pieces. So for that, we have this primitive called async stream, and it lives in not in Finatra or Finagle, it's in Twitter util, which is wonderful reusable code from Twitter. And yeah, it has many fans, and you know. So an async stream is really, it's practically a lazy list of futures. It's slightly different, and I'll tell you how in just a moment. But let's just go over several important properties. One is that it's immutable, so it can be shared by multiple threads. When the stream is modified, it doesn't get updated. It creates like a new version of itself, which points to like the old version. So there's always this previous version that sort of just stays around and gets collected or whatever. So that's called persistence. It's also lazy, so the tail of the stream, if you don't need it, then it never gets evaluated. So that's really important when processing infinite inputs. So like, let's say, like a stream of events or something. So the basic shape, I just took that from Wikipedia's linked list page, but it sort of applies here. You have these cells that have two parts to them. The first part is the value, and the second part is a pointer to the rest of the stream. The only difference between let's say like a normal like Scala stream and an async stream is that the tail, the pointer, it's behind a future. So it requires like a rendezvous between whoever is supplying the future. Cool. So some basic constructions to introduce you to the async stream. It should not look alien at all. There's an empty stream, which is given by just empty. And you can make streams of strings, streams of ints, and you can convert other things into a stream, like sequences and options, and also futures. So this is the special one. So how do we do this? How do we take a future and make it into an async stream? I'll get into that just in a moment. So because of all these things, you can use them in a for comprehension, and it behaves just like a list flat map. So just to go through this, we had 1, 2, 3, 4, and it's as if these were like seeks. We'll get like a 4, and then 2 and 3, and then 1, and if we sum all of them, we'll get like this 7 and 8 if we convert it to a sequence. I hope that's followable. Anyway, so let's have a look at how it's implemented. So as I said before, it's a chain of these cells where one part is the value and the other part is the rest of the stream behind a feature. So how do we do that? Well, we take this thing called node, so a type node that has two constructors. One is the empty node, which is like that last box there. So that's what it represents. And then a cons, which is the value and then the rest of the stream in a tail. So you can see the type of tail is async stream. And how we define async stream is it's a wrapper of the future of a node. So the node type is actually hidden, and to use async stream, that's like the public interface. You don't have to think about node at all, but that's how it's implemented on that's like the internals of it. So to sort of illustrate all of this, I would ask you to think of a queue API. So we have something like this in Finagle called async queue, in fact. But this can work for any kind of queue that you have some sort of receive or poll, and it returns to you a future of something. So you can imagine that an async stream is just a bunch of these operations, like sequenced. So you can turn any sort of reading from a socket or, I don't know, reading from a queue like this into a stream. So like right at the bottom there, that's how you convert it. You take receive, which gives you a future of string, but from future gives you an async stream of string. And then you concatenate it with, by recursing on received. But that will only get called if it's demanded. And that's important. So what you get is this repeated calls to receive. And with that, you can imagine creating like an echo server of sorts, where like the basic component of it is that you take this one stream of messages that you've received, and then you just write them out again to some send API. And you can do that just with a for each f, which is a for each that's specialized to a future operation. So what happens here is when the poll, the receive completes, we send it into this, we write it into this send operation. And when that completes, we call poll again. That's the mechanism for this. You can imagine that to transform the messages, you'll just map it. So here is that same echo server, but with all the messages uppercased. So it's, I guess one of the benefits to this as well is just to be able to program, to sort of like structure your program in these modules, and then you can like map the pipeline through them, ending in some effect, which is send in this case. So I want to say lastly that async stream is pretty much just like a list, kind of just a little bit of its API. You have all of this stuff like for each, take while, drop while, concatenation, and you have all of the monad interfaces like flat map, and then you have the functor interface map filter. So you can use this like in for comprehensions, and there's like tons more stuff. And I think I'm gonna pass this back to Steve, and he'll tell you how, he'll connect how this is used in Finatra.
All right, thanks, Neuman. So we started integrating async stream into Finatra in early June, and we released response support in the milestone 2 release. So that allows you to return an async stream from a controller, and the async stream will be automatically rendered either as bytes, if you specialize a way to convert into bytes, or it'll be seamlessly converted into a JSON list. And today, we merged experimental support for parsing requests with async stream. So the way that looks is instead of a sequence of tweets, you'll now see there is an async stream of tweets. Notice that now that we have the tweets, we can for comprehend over the tweets. So now for each tweet, we can call the database save method. That save method returns a future. We convert that future into an async stream. We then get a saved tweet, and we're able to then yield the ID that the database generated for that tweet. So this is now a fully streaming, non-blocking API where you can post an infinite list of tweets in, and as each one is saved, we'll stream out the IDs. Likewise, in the bottom, you could post a list of IDs. We'll look up each ID one at a time. If the ID is found, it'll be returned. If not, it just won't emit anything for that running. And the way that happens is database get returns a future option. And when you call toAsync stream on that, if it's a future none, it's just an empty async stream. If it's a future sum, it's an async stream with one element in it. Here's what the output looks like if we were to post a list of tweets to that endpoint. You'll notice we return the transfer encoding chunked header. And then as we're writing, we immediately started receiving the beginning JSON list. We wrote about 5 tweets, and then we read the ID of the first tweet. And then at that point, the operations are interleaved. So the way this works under the hood is we start out reading from request.reader. So that's an asynchronous way of reading bytes from the Finagle request. We turn that into an async stream of buffs. So buff is our encapsulation of bytes. You could see that the way we receive those might not be on proper boundaries, and most likely is not on proper JSON boundaries. So we parse that looking for valid JSON objects in the list. So the top 3 buffs will end up turning into 2 buffs delimited on the elements in the JSON array. And then for each one of these guys, we'll object map it to the case class. So we're streaming each tweet, but for each tweet, we're OK loading the entire tweet into memory and object mapping that. So it's kind of this best of both worlds. If you had to stream parse every individual field of the tweet, that would be pretty onerous. But this kind of gets you a good middle ground. And in terms of future work, we're hoping to have a similar API for multi-part file uploads so that the controller can ask for an async stream of buffs. You could then, in this example, maybe sanitize the bytes in a certain way before, let's say, you stream them to a file or stream them into your database. And that is all. Any questions?
Based on the case class that you're parsing for, or are you just matching any blind object that you get and then you're going to fail to match that and keep going? How does that work?
We first take each individual element out of the JSON array coming in. That element is then compared against the case class. So that could be an arbitrarily complex, case class with inner case classes, but we're just kind of doing a trivial JSON list parse first, and then doing the parse. And one of the things we're planning on adding is an ability to ask for an async stream of tries of, let's say, tweets, so that if one of them fails, the whole thing doesn't fail.
So when you're parsing, are you operating off of like a buffer? And if so, does it know that for for example, if it has 3 tweets already parsed, that it can run all of those steps on like the same thread or something?
For each buff that's read off of the request that essentially Netty is giving to us, we'll find however many full JSON objects we can. So if in that buff there were 5 tweets, all 5 of those tweets would kind of be processed at that time in that kind of iteration. But if a full object isn't parsed and we have to wait until the next request to get a little bit more, that's what's saved in memory, just so the next time it could kind of fill it in.
Okay, one more question.
How do you set the chunking boundaries on the outgoing stream?
The chunking boundaries. So I think what's probably happening, was there a write example? Because you can't write to an async stream, so I'm assuming that you just produce like one element each time. And then whatever that gets parsed into, I guess, is some sort of buff, and then the buff gets written to the writer, which is kind of an abstraction of the queue that wraps the socket. So it would just be that buff. And then that would get written to Netty as a chunk, like an HTTP chunk.
Yeah, so
And then,
like each JSON object.
yeah. And then Netty will do whatever